So looking at number 5 on page 54, question is a rectangular box with no lid is to be constructed from 12 square meters of cardboard by cutting square notches out of each of the 4 corners and folding up the remaining sides. We want to find the maximum volume that such a box can have. All right, so we know volume, by definition, of a box, length times width times height. Right. We need to come up with dimensions for this, what I would imagine is going to be a multivariable function that correspond to that. Right. Not only that, that multivariable function should somehow have a graph that looks something along those lines. All right, so let's start off with a diagram that's a little bit more reasonable, like a rectangle with notches cut out of the corners. See if I can do that without screwing it all up. They're like, these aren't notches. You're right, they most certainly are not. Hopefully when all is said and done, they will be. That's the plan anyway. Square notches, I believe that's what I said, yep. So let's try to make those notches look somewhat square. Okay, I mean, it's not going to be perfect, but it's all right. All right, so each one of these little square regions here is what we're working with. Those will be cut out, and those flaps will be folded up. You know, this is the same general setup as it would be in a pre-calc or algebra class, or calculus, or every other math class that you've ever taken in your entire life. All right, so what we're trying to do here is, if we're given this piece of cardboard that's 12 square meters, we're trying to find the dimensions that would represent or that could be multiplied to give us the volume. All right, so let's call the dimensions of the square notches, let's call that X. All right, now the area is equal to 12 square meters. Now I honestly have no idea what the length of each side is going to be. I just know that they have to multiply to equal 12. All right, so let's call one of them Y. I've already used X, so let's call one of them Y. Poor quality Y. Not much better, but doable, or I'm willing to live with it. Now, if I fold up the 4 flaps here, we're going to end up with this side, this length here, being the length of one side of that folded up figure. All right, so we have 12, geez. We have Y minus a couple of X's, this one and this one. So I can call this, well, if I don't accidentally put my hand on that tool, I could say Y minus 2X. All right, now the other side, again, I don't know the length of either of them, but I do know that it has an area of 12. So if I'm calling this one Y, and they both have to multiply to equal 12, the only other possibility is that this would have to be 12 over Y. 12 over Y times Y would give you a 12. All right. So the other dimension here, or another dimension, would be 12 over Y minus 2X, because again, we're taking the whole length and subtracting off of it the length of each of these corner pieces. All right, so if I were to take those lengths, so this length, I didn't want it to snap up there, jeez. Let's see if I can get it over here. I just want it to be roughly the same length. It doesn't have to be perfect. close enough. And I can take this length over here. That would basically be the base of the rectangular solid. Just piece it together, creating that rectangle. Give it some height consistent with the length of X. All right, now that part I'm gonna have to do it in sort of a perspective drawing. It's gonna be pretty terrible, as you've come to expect. So this just kind of on an angle. I just want to pitch it a little bit. It's gonna, like I said, it's gonna be a little bit off. I mean, what I really said was it's gonna be terrible. And I hope you'll hold me to that. Let me get my braces in here. And now we have the box. All right. So 12 over y. Oof, I'm getting dizzy just looking at it. 12 over y, y with a height of x. All right. So the volume, length, width, height. All right. Undo, undo, undo. Length. Width. Height. Using a technique I like to call the right way. Yeah, I don't know. I just saw these guys and I just went after it like an animal. All right. So, but yeah, it's the length and width of the box, not of the overall piece of rectangle. I guess. I guess that works, but what I meant to say was piece of cardboard. All right. So we have this volume formula. Volume is length times width times white. Length times width times height. Cannot speak anymore. This is a quicksand. Make one mistake. Things start getting out of control. So anyway, I have a multivariable function that I'm looking to maximize. So I'll find derivatives. Now, it's just a question of, do I want to jump after it right now using some variation of the product rule, or do I want to multiply a little bit first and see where that takes me? You know, if we distribute it out a little bit, it might end up cleaning up somewhat. And if it does, then we could save ourselves a little bit of effort, time and effort when it comes to finding the derivatives. All right, so let's do that. All right, so we're looking at 12 over y times y is 12. The outers would be, well, it's not going to be pretty, but I'm going to write it as minus 24xy to the negative first, minus 2xy plus 4x squared, and the whole thing is multiplied by x. So we're looking at 12x minus 24x squared y to the negative first minus 2x squared y plus 4x cubed. I prefer to write it like this with the negative exponent, just so we can make use of the power rule rather than having to get into quotient rule or any variation of some more complicated process. All right, so we need first order partials with respect to x and y, so we'll start off with the x, so 12 minus 48x y to the negative first minus 4xy plus 12x squared. All right, we're gonna have to set that equal to 0 and solve. But before we get there, let's do first order partial with respect to y. So we're looking at, well, this would cancel. So we're looking at 24x squared y to the negative second minus 2x squared plus 12. Oh, well, actually, the last one will cancel out. That's in terms of y, or we want it to be in terms of y. All right, so we get some algebra ahead of us. No way to slice it other than just come out and say it. So I'm going to minimize. That just makes it sound fancier than it really is. I'm going to shrink down my diagrams and move some stuff over. All right, so let's focus on the x part of it first. All right, so I'm going to set it equal to 0. A little too thick. Let me just bring that in. 0 equals, now I'm going to rewrite it with negative exponents. I'm sorry, without the negative exponents. So minus 48x over y minus 4xy plus 12x squared. All right, I'm going to run through the y. So 0 equals 12y minus 48x minus 4xy squared plus 12x squared y. And I'm going to do the same thing with the second equation. Set it equal to 0. 24x squared over y squared minus 2x to the second. All right, you see there's a common x squared there, so that's going to be useful. So let's get into that. All right, but before I do that, let me clear out that y squared. So I'm going to multiply everything by y squared. So 0 equals 24x squared minus 2x squared y squared. All right, so just focusing on this one for a second, I can pull out a 2x squared. And then when I pull out a 2x squared, I'm left with a 12 minus y squared. All right, so I'm looking at x equals 0. Let me not skip steps. 2x squared equals 0, making x equals 0. All right, so I still skipped a step, but I mean, it's like an obvious step, I think. All right, and then 12 minus y squared equals 0, which makes 12 equal to y squared, which makes y equal to plus or minus rad 12. I'm actually going to leave it like that for the time being, because we could simplify it down to 2 rad 3, but let's see if there's a reason to do that. You know, we might find out it's not really worth it. Right? So we have the other partial to worry about here. All right? So we kind of left that off, a little bit of a cliffhanger here. So using this equation, I now have to evaluate that for when x is equal to 0 and x is equal to positive root 12 and negative root 12. So I'm going to make a little note here. At x equals 0, we're looking at 0 equals 12y, and that's about it, right? All right, because if you replace all your x's with zeros, all these terms will cancel away and you're left with y equals 0. All right, so we'll have one critical value from that. At y equals root 12. And something to bear in mind, there was no way to solve, well, don't want to say no way, there's always an opportunity, but we didn't have the kind of common factors that we had for the other equation that would have allowed us to separate out or at least easily separate out the x and y's. So to try to solve this one for a constant value for x and a constant value for y was not practical. Right, so in this case, we're looking at 0, 0, let me turn on my pen, and then write correctly, 0 equals 12 root 12 minus 48x minus, now if I put in a root 12 here, I'm going to be looking at root 12 squared, which is just a 12, times the negative 48 is going to be negative, gave the answer in the question, times negative 4 is negative 48, so negative 48x. And then we'll have plus 12 root 12x squared. All right, so we actually do have some common factors here, which make, call it like terms that can be combined, but it's not pretty. But it is something that's manageable, somewhat manageable. So let me rewrite 12 rad 12 x squared minus 96x plus 12 root 12 whole thing equals 0. Now it's just a question of what this is going to spill out for us. And, you know, it is quadratic, so it's a matter of preference how you want to go about doing things. We could look at it as something, you know, I'll call it quadratic formula-ish. But you could also give it a shot factoring. I mean, my preference is, in a class that's not an algebra class, to try to just get the job done as quickly as possible, requiring the least amount of effort. And in most cases, that's something like Desmos. All right. Now, it may not play out because if the numbers aren't clean, then you end up with something like this, in which case it tells you at a minimum that you have to do some radical work, as in quadratic formula, but that's information in and of itself. All right, so x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. I definitely didn't need a radical that long. I mean, you could go completing the square if you want, but in my experience, when I offer the choice, most people opt out when it comes to that. So 96 plus or minus the square root of 96 squared, the negative's going to zap away, minus 4 times 12 radical 12, that's the a, and the c, another 12 radical 12, as it turns out, all over 2a, so 24 radical 12. All right, so we're looking at 96 squared minus 4 times the a value times the c value, which you could actually just write, it's 12 times 12 times 12, so 12 cubed, but you know, you could also just write it in. Oops. So root 2304, not too pretty. All right, so that 2304 is pretty substantial. And so if we're going to try to simplify this, that's going to be the key to everything. So you can go about it a couple ways. When it comes to Desmos, I like using a table approach. You know, you just put in a bunch of values. And then make the second column the whatever the radicand is divided by the first column. So it gives you a list of factors between the second column and the first column that'll actually, oh, sorry, squared. It's kind of important that it's squared, right? So this will give you a list of values that will be divided evenly by the first column squared. All right, so it gives you a list of perfect square factors. All right. What I also like to do, and I'll just show you really quickly, is throw an intermediate column in there where you actually just square the first column, and then just as a separate step, 2304 in this case, divided by the x1 squared. And then you can see here each pair of values is a set of factors, right? As long as they're whole numbers. But as you can see, it doesn't take too long for you to realize that, oh, 2304 must be a perfect square. So you could always just try that first and see how it goes. I just figured I'd show this technique just so you have it. All right, so the square root is 48. All right, so although, yeah, as it turns out, how nice. You know, so anyway, we got 96 plus or minus 48 over 24 radical 12. And you know, at any point you can simplify the radical 12 prior to this moment. I'm going to actually simplify it now because this becomes a 2 radical 3. So I could say 96 plus or minus 48 over 48 radical 3. This way I could simplify the numerator further, you know, because each of the coefficients are divisible by 48. So we're looking at 2 plus or minus, really a 1, over the square root of 3. So we're looking at possibilities of 2 minus 1 is 1 over rad 3, or 2 plus 1, 3 over rad 3. Either way, at long last, we get some values. All right, so we got a list of critical values here. We got a list of critical values a mile long. So 0, 0. We got, well, the radical 12 for y gives us these possible values for x. So we would have a 1 over radical 3, or a 3 over radical 3, each corresponding with a radical 12. All right, now we could do all the same work again, or similar work, for the case where y is equal to negative radical 12, but that's going to end up being irrelevant if you really think about it, all right? Because y is the length of a side. Use an arrow here. It's the length of a side, so why would it be negative? You know, it's a geometric figure, so not possible. All right, and so with that in mind, it turns out that the x equals 0 wouldn't be possible either, because if we're starting off x equals 0, y equals 0 wouldn't be possible, because 1, it would give us undefined as part of the domain, 12 over 0, but also, more importantly, what kind of box are you going to have when the original dimensions involve a y value of 0? All right, the length of one of the dimensions is equal to 0, so that's irrelevant. All right, so another unnecessary value. So we're looking at 1 over radical 3, comma, radical 12 versus 3 over radical 3, comma, radical 12. Now, if we know that it's going to come, our solution is going to come from one of these two values, then it's it's really a question of, aside from, the obvious, well, which one is it? Which method are we going to use to verify? Do we want to go with the second derivatives test? Based on what we've seen with the first derivative, it's not too pretty. The other alternative would be to go back into our original function and evaluate each of these two numbers, really. So if I take my two critical values and go back to the original model, Right, whether it's the distributed out form or not, I'll take the one that's undistributed. So the factored form, the original, what we started with. And then evaluate this for these two, no, I lost a paren in this. For these two critical values, I would just be looking for the one that gives me the larger value. All right, so, because I have an x and a y, so I'm looking for v of 1 over rad 3 comma rad 12, v of 3 over rad 3. Oh, and by the way, 3 over rad 3 is equal to rad 3. So you could actually simplify things a little bit. We don't always have to make our lives more complicated than they need to be. So I very often say you don't need to rationalize a denominator, but sometimes you want to rationalize a denominator just because it's going to be a little bit easier to substitute in. So in the case of the 1 over rad 3, I wouldn't rationalize, but in the case of the 3 over rad 3, I actually would because it gives me something simpler. All right, so then it's just a matter of popping these numbers in and seeing where it gets me. So I was actually going to start handwriting it, but you know what I can do is I could just go to Desmos now because, again, it's just the value that we care about. All right, so you saw a little table technique, a little fun table technique. What I can do is write my multivariable function in terms of a and b. I've done this a bunch of times. The reason why I like doing this again is, I want to use a b there, is because it allows me to pop in multiple values. All right. And it understands the fact that there's two quote-unquote variables being used. So b minus 2a, b's instead of y's, a's instead of x's. All right, just check it for consistency. Looks like we're good there. Tap on all so we get the sliders. And then, if you want to reorganize it so that it actually kind of flows a little bit better, that's not a bad idea. 1 over rad 3. That's not a 3, that's a 3. And then a rad 12, or 2 radical 3 if you want. All right, so we're looking at about 3.0792. And then rad 3 versus another rad 12. This time straight up 0. We're going to get a volume of 0 for that one. Well, I wouldn't think that that's going to be the maximum volume. All right, so it looks like our winner is the 1 over rad 3 comma 12. So the dimensions, we just got to be careful. Find the maximum volume that such a box could have. So the volume, max volume here would be meters cubed. That's all they're asking us for. All right. If they said dimensions, we'd have to be really careful not to just say it's x by y, because those aren't the dimensions. The dimensions are 12, well, it's y minus 2x by 12 over y minus 2x by x. All right, so there's a lot more going on there than it might seem, at least at first glance.